Okay, the last thing I want to cover, and this actually is kind of related to ionic and precipitation reactions and the whole discussion of ions in water solution. But it's not a reaction, but it's a topic that I want to kind of cover real quick because it's kind of an intro to organic. And that is that some solids, when you mix it in water, actually dissolve, but they don't dissolve in an ionic way. But they do dissolve, and so I want to kind of talk about that a bit. And this is more like a discussion about the whole water and the polarity of water thing. But again, it's very common in organic. So I'm going to draw a compound called glucose. You all know what glucose is. So glucose has 4 C's, and it has that has an OH on one side. Now it's connected to a C that has an H, and an OH, and it's connected to a C that has a double O and an H. I think that's glucose. Pretty darn close, at least. I might be off by a C or so. Glucose. Okay. We can take that and take a chunk of glucose. It's a solid. And dissolve it in water, or put it in water and stir it around, and visually speaking, the glucose disappears. It's almost like what happens to salt when you put salt in water. But what's happening when the glucose dissolves, which again that's how we observe it, is it's not turning into a set of ions. It's not splitting into ions like the ionic salts did, like sodium chloride or calcium chloride or even sodium carbonate, which we talked about in the last videos. But what's happening is that it's mixing up with water, and if you remember back to the polar nature of water, is that there's so many sites here that are almost like water-like. If you look at all these OHs here everywhere, there's OHs kind of everywhere, and there's H's nowhere. And so the water molecules that you're dissolving it in kind of align itself with various spots in this glucose molecule. Effectively, I'll put a couple more here. Essentially, water is acting like a wedge with respect to the bonding, the solid bonding of this chunk of glucose, and it's taking a single glucose molecule, if you will, and surrounding it by waters. And it turns out, electrically speaking, and essentially from an energy standpoint, the glucose is happier to be surrounded by water molecules attached to all of its little slightly positive or slightly negative parts of its molecule than it was being connected to the rest of the glucose solid. Okay? And so this is what it means when you dissolve sugar in water, and you can't see the sugar solid anymore. The sugar's still there, and it has not divided into ions. It's still a non-ionic mixture, solution in the water, but it has dissolved because electrically anyway, it's happy being divided up into small glucose molecules as opposed to being part of a larger glucose solid lattice. Down at a low level. Okay. Now, the nature of this, though, in solution is a whole lot different than the nature of these dissolved ionic compounds. One aspect, and I think it's covered in the first section of the book, is that typically when you dissolve an ionic compound in water, it actually becomes able to conduct current. It becomes what's known as an electrolyte, and that is because you have plus and minus particles floating around in the water. If you put an electric charge on that solution, the ions will tend to, the positive ions will gravitate towards the negative pole of the electrode, and the positive ions will go, or whichever, and the reverse will go to the other. And essentially what that means is that the solution itself becomes like a charged, able to flow an electrical current through it. This is not the case when glucose dissolves. So because glucose, when it dissolves in water, there are no plus and minus charges in there. It's still it's still basically a neutral liquid, and so it does not conduct electricity. It's not an electrolyte. Okay, wanted to point this out, and because it only kind of begs the questions like, with sodium chloride, for example, we can easily visualize what happens when it dissolves. It truly splits and it becomes something else. It becomes sodium in one part of liquid and chloride in another, and it's no longer the same. When you dissolve a covalent compound like glucose, however, that doesn't happen. It doesn't split, but it just doesn't become a solid anymore because it's happier being surrounded by the waters. Okay, and as we all know, when you try to dissolve sugar in water, there's a limit to how much the sugar will dissolve in the water. If you start pouring in too much sugar, you'll find it doesn't dissolve anymore. It becomes saturated, and it becomes saturated because, well, there's just not enough water molecules around to satisfy the electrical pattern that compels glucose to split apart from its other solid glucose molecules. Now, we'll talk. I think we may talk about solubility a bit more. I mean, one way of solving this, as you know from a kitchen, is if you actually heat up the mixture of saturated water and glucose. If you heat it up, it'll actually dissolve even a bit more. And so there are things like that you can do to kind of affect the solubility of compounds. In this case, like heating. Okay, that was all I wanted to do for this one, and this kind of covers the whole non-ionic solutions in water.